Hi everyone, my name is Emir İpek. Today we will present our project to you. The name of our project is Follower Unmanned Aerial Vehicle. We carried out this project as a team of four. You can see my teammates and their tasks. Selim, Tolga, I and Buğra. Also, you can see the task distribution more clearly on this slide. So, why did we decide to develop this project? Commercial tracking drones are expensive and often require constant operator input. There is a need for intelligent, autonomous and cost-effective UAVs in fields like surveillance, sports and emergency response. Now you can see our problem statements: poor quality, high price, imported products and poor performance. Our design goals include real-time frame analysis, low latency data transmission, modular architecture, autonomous following capability, lightweight and poor efficient. Now you can see the marketing requirements: portability, cost efficiency, affordable, lightweight, and etc. Also, you can see the engineering requirements on this slide: weight and balance, image processing, power system, electronic design, control and communication, and etc. Now you can see our basic design on this slide. Commands from the remote controller and images from the camera are sent to Raspberry Pi. And Raspberry Pi processes the data and sends commands to the flight controller, which then activates the motors to start tracking. Also, you can see our detailed design on this slide. Raspberry Pi classifies the visual data, processes the image, and sends motion commands to the flight controller. The controller initiates tracking based on these commands and generates PWM signals to drive ESC. ESC then powers the motors to enable flight. That's all from me for now. I will now hand it over to Selim.
Details of implementation. Here is the overall system architecture of our project. Our system consists of a Raspberry Pi 4 and a Pixhawk flight controller. A camera is connected to the Pi via CSI interface, and the Pi communicates with Pixhawk over UART. The Raspberry Pi handles real-time image processing while Pixhawk executes the flight commands. Hardware connections. The diagram shows the system's connection flow. The camera sends image frames to the Raspberry Pi, and the Pi processes the frames and sends velocity commands to Pixhawk via UART. All communications happens in real time. This is the physical hardware setup on the drone. Pixhawk is connected to the 4-in-1 ESC, which drives the brushless motors. The Raspberry Pi and Pixhawk are mounted on the frame, powered by a 5200 mAh LiPo battery. Color detection algorithm. We used HSV's color segmentation to detect red colored person. Frames are converted to the HSV and a mask is applied to the isolated red areas. A bounding box is drawn around the target and its center is used for navigations. We adjusted to HSV thresholds by testing under lighting variations. Upper and lower HSV bounds were optimized to reduce fault detection. This made the system stable enough for basic training. Also, this lightweight method avoids the need for any AI model. Pixhawk configuration. Pixhawk is configured while using Ardupilot firmware. Guided mode was enabled so it can receive velocity commands from the Raspberry Pi. Future improvements. We plan to upgrade processor and add sensors like LiDAR and ultrasonic models. These additions would improve obstacle avoidance and make system more autonomous and reliable real-world applications.
I will give information about testing and demonstrating. We conducted a three-stage test of process to evaluate the functionality of our system: simulation, indoor, and outdoor tests. Firstly, simulation tests were performed in a virtual PX4 environment with Mission Planner. Direction commands were generated by Raspberry Pi according to the red target detected with the HSV-based algorithm, and the effects of these commands were monitoring via Mission Planner. This test was a critical step to verify the control logic before moving on to physical flight. For indoor tests, flights were conducted in a controlled room with stable lighting. The target were red close to ensure consistent detection using HSV segmentation. We calibrated electronic speed controllers for proper motor synchronization. PID parameters were tuned to achieve smoother yaw and throttle control. In outdoor tests, under the natural daylight, a team member wearing a red t-shirt and act as the target. The drone with the camera angled about 45 degrees maintained an average distance of 5 meters while following. Minor instability appeared in shadows and sudden movements, but overall performance was satisfactory. Real-time detection and tracking were successfully verified during these tests. The systems showed sufficient performance for real-time tracking with an average processing speed of 15 and 20 FPS. The target was successfully tracked with HSV color segmentation and the system responded instantly to the target's location. The red target was tracked reliably both indoors and outdoors. UART communication working stably and the drone performed a stable flight thanks to the PIXAV PID settings.
So as you see on the table, we have approximately spent 25,000 Turkish liras for our product, and we are expected to sell for 30,000 Turkish liras, and which makes $772 in today's currency. So when we compare our product with the most popular ones on the market, you can see we have a competitive price, and we can easily satisfy the expectations. When it comes to our commercialization strategy, so we are targeting users who can be recreational drone makers and amateur filmmakers or sports and fitness trainers. So we basically divided our sales channels to 4. We prepared to create the official website for our products, or we can use online sales channels such as Amazon, or we can directly contact hobby and drone shops, or we can use B2B methods to directly sell our product to companies. So certification and standards, they are 2 international standards, IEEE and ICO, and one for the United States FAA and one for the Turkey DGCA. So we cared these standards and certifications when we produce our products. And they are basically 4 safety features for our product. For autonomy, we have return to home setting. For emergency, we can real-time manual override for emergencies, and we already made our calibrations, and we can easily switch the modes from autonomous to manual. And the legal issues are also important. Like I told you, FGZK cares and makes the regulations for drones, and there are some registration requirements for our drone, and we can need certain activities like pilot certification for certain activities, and they are restricted flight zones and airspace flight zones for our drone. We care this when we are producing our products. And that's all for us. Thank you for listening.